The speaker should work.
Thomas access? It's your laptop?
Yes. Yes.
Okay, so welcome everyone to the second session of the morning. I'm Antoine Klein, and I'll be chairing. So the first talk we will have is the next chapter of the white paper about supermassive black holes and massive black holes, which will be presented by Elisa Portolas, which is here, and Pedro Capello and Melanie Hamsins, which are you have an hour.
Thank you for a nice introduction. Yeah, so it's a real pleasure to be here and to have the opportunity to present you this very big amount of work we've been doing together. And first of all, I really want to stress that, this is the full author list of the white paper, and the names that you might see highlighted, maybe you cannot see very much, but very many of those are highlighted, and these people contributing to chapter 2. So we want to take the chance to thank you all, because I think it's a lot of time and effort made by people. So thank you for that. Also, as mentioned by Tassos before, we want to have the chance to properly give credit and give references to all the works, because there are too many, but you can find everything on the white paper if you need it. Okay, so let's start. First of all, we probably all know that one of the main purposes of LISA is actually to detect the merger, the gravitational wave-induced merger of massive black hole binaries. And in particular, LISA will be unique in the fact that it will be sensitive to the merger of massive black holes in the range between 10 to the 3 or 10 to the 4 all the way up to almost 10 to the 8 solar masses, and depending on the masses, it can probe the population of merging binaries up to very high redshift. So this will be like a great way to actually, first of all, bridge the gap between the two better known populations of black holes, so the stellar ones and the supermassive ones, so really piercing between, and also constrain the growth of what are today supermassive black holes. Very debated. Okay. And so the talk, actually, our presentation is divided in the following way. So first of all, Melanie and Pedro will tell you about how we can really maximize the scientific outcome of LISA through our theoretical modeling, especially understanding how do the massive black hole binaries evolve and reach their way to coalescence, and also the massive black holes, how they grow, what is the population we can infer from population synthesis studies. And later on, I will do my best to also present you the synergies that LISA can have with other observatories, both in electromagnetic, gravitational wave, and astroparticle regime. So now I leave the stage to Pedro to start his presentation.
Thank you, Elisa. Let me just share my screen. Do you see it?
Yes.
And my mouse as well? Okay, great. Okay, so in the next 15 minutes, I'll try to give you a very brief overview of our collective knowledge of how supermassive black holes can travel several kiloparsec down to the binary formation and beyond. So the review of this part was written by many people, and you can see the list up here on the top. And basically, we're trying to understand all the mechanisms that actually can help two supermassive black holes that start in their respective hosts at distances of about 100 kiloparsec or more, until they actually reach the gravitational wave dominated phase, so down to milli and microparsec. So our knowledge started exactly 40 years ago with this plot that you see on the left by Begelman and collaborators. And amazingly enough, this plot is still mostly correct. We have three main phases: the dynamical friction phase, the stellar hardening phase, and then the gravitational radiation phase. And the timescales depend, of course, on many, many properties of the halos, of the orbits, of the masses of the black holes, their mass ratios, and so on. And so basically, in this section of this paper, we try to list all the mechanisms that can help, but also those that can hinder the binary formation, and also list all the things to do for the next 10 years before LISA flies. So we started from this plot from 40 years ago, but of course, in the past 40 years, we managed to know a lot more, add a lot more nuances to our knowledge, and much nicer plot can be shown here, where we basically show the effects of many, many effects, the effects of many, many mechanisms like bars or clamps or mini disks or circumbinary disks, together with their spatial range of importance. So let me start with the first phase, which is basically the large scale phase. This is the dynamical friction. We start from the dynamical friction in collisionless media. This is obviously a mechanism that has been known for almost a century. Basically, you have dynamical friction that can be described as a local event using the Chandrasekhar formalism. But also you can describe it as a global event, because there is also a global exchange of angular momentum and energy between the incoming black hole and the main host. So in many cases, we've been using the local description, the Chandrasekhar description, but it is important in the next few years to account for the corrections to the dynamical friction timescale introduced by global torques, to have a much more robust estimate of this phase. Which is very important because actually it's the phase where the black holes spend most of their time. And of course, it depends on many aspects of the system. So on the density of the system, on the masses of the black holes or their mass ratios. And so we need to study many, many systems in order to get more robust estimates. Initially, these estimates were provided for very, very simple profiles, for example, singular isothermal spheres. We know, though, that systems are more complicated than that. They're usually shallower, so they follow the NFW profile or even chord profile. And of course, this has an effect on the dynamical friction timescale because the density is one of the most important quantities that basically give us the time scale. Not many studies have been done in recent years on the study of dynamical friction in shallower inner density profiles. And the few that have been done, for example, the recent ones by Tamfal et al., they only considered collisionless systems. And of course, it is important to also add gas dissipation, stellar feedback. So I think more studies have to be done in this respect. Another simplification that is usually done is that we include only slower stars than the black hole. But of course, faster stars in some systems may be important for the dynamical friction force. There has been work done, of course, in this respect by, for example, Antonini and collaborators, but in very idealized systems. So we should also assess the outcome for more realistic profiles of the nucleus for for these particular systems here. And finally, the systems are not only collisionless, they're also collisional. And so we should always also include the effects of gas. So this gaseous dynamical friction has been studied, of course, in many respects, for example, by Ostreicher and then by many other people later on. But of course, it depends a lot on the multi-phase state of the gas, on the dynamics and on the thermodynamics of the ISM. So a lot of investigations with realistic gaseous and stellar environments are needed for this. Moving on, we know that systems are not spherically symmetric, they're not smooth, they don't follow a power law profile, but they have a lot of asymmetries and even worse. So for example, we need always to include also the effects of disks. These disks can be large scale. So we're talking of galactic disks of the order of 1 to 10 kiloparsec. But the disks can also be smaller scale, like circumnuclear disks, so about 100 parsec or so. And so we should account also for the multi-phase nature of the ISM and star formation in the inner parts of the region, especially in circumnuclear disks. Related to gas, we should also include always the effect of feedback. And recently, many studies have shown, actually a few studies have shown the existence of this so-called negative dynamical friction, which basically goes in the opposite direction as the normal dynamical friction we all know about. But this is just the beginning. A much wider range of scenarios is needed to really understand the implications of negative dynamical friction. Here in the plot, you can see that, for example, in one semi-analytical study by Lee et al., they basically showed that if you include this negative dynamical friction, the massive black hole pairing probability decreases significantly. And actually, in the bottom plot, you see that for 10 to the 6 solar masses, which is more or less the target range for LISA, the reduction, the decrease is about 1/5. So it's potentially very significant. And of course, we know that systems are not smooth. They have a lot of instabilities, both global and local. And recently, there have been studies that included the effects of bars and also the effects of clamps. And the result is basically that the pairing is very stochastic. There are some cases where the black hole is aided into going down to the center of the host, or sometimes it's scattered out by clamps or even by the bars. And a lot of studies should actually be done in order to understand a little more what are the effects of these asymmetries and these basically instabilities. We should also have a better understanding of the bar fraction versus redshift and how many bars there are in mergers, for example, which is obviously the most important system that we care about for LISA. And also we should have a better understanding both observationally and for simulations of clumpy galaxies in order to understand how many clumps there are per galaxy, how massive these clumps are. So moving on, basically, just to summarize this first part of the talk, the question has moved to, is there a final parsec problem, which I'll talk about in a second, to is there a final kiloparsec problem? Because as you just saw, there are several mechanisms that can actually hinder the formation of a black hole pair even at distances that can range between 100 parsec and a few kiloparsec. This can be due to clamp scatterings or, for example, chord inner density profiles. And also this is aided by the fact that observationally we see some wandering off-center supermassive black holes. So we should understand more if there is actually a final kiloparsec problem, because of course this could be a big problem for the LISA event rate. So more detailed and realistic characterization of massive black holes in a variety of systems at all redshift is needed in the next 10 years. Now, if we manage to overcome all these problems, then we can go to the next stage. And that is the stage where you have hardening in stellar environments, where you basically have three-body scattering, helping the hardening of the binary. For a long time, people thought that there was a final parsec problem, because basically this three-body scattering ejects stars, and then the loss cone, which is basically the phase space of stars with low angular momentum, is depleted. But this problem turns out to not be such a big problem, because it was found only in perfectly idealized spherically symmetric systems. And it's been shown then in triaxial systems, for example, like the ones shown here in this slide, which are basically a natural outcome of the merger of two stellar bulges. Then the loss cone is constantly replenished. So the final parsec problem is not a problem. However, all these studies have actually given a very wide range of timescales. So a lot of work is still needed to understand the relation between the timescale of this mechanism and the properties of the host, because we can go from 10 to the minus 2 gigayears, even to 1 gigayear easily, depending on the properties of the host. And this is related also to the eccentricity of the orbit. Several studies have been performed recently to actually have a better understanding of the eccentricity evolution of the orbit with different results, with eccentricity that can grow or can decrease, depending, for example, on the mass ratio. So more work is needed.
Right, bye.
Okay. And to complicate matters even more, most of these studies have not included host rotation. And of course, the host rotation is important because rotating or counter-rotating systems can decrease or increase the interaction time between the binary and the stars. And also the substructure in galactic nuclei is very important. You could have low mass structures, like low mass clumps, that are probably not too important to move the black hole, but they could still create some Brownian motion. But the massive perturbers can actually interact with the hardening binaries, and they can be important for many respects. They could deflect the binary out of the center. They could deflect stars towards the binary. And if these massive perturbers are stellar clusters, they could even give stars to the binary. So we need to basically pinpoint the rate at which these massive perturbers may interact with the massive black hole binaries in many host environments. Now we get to the more dirty and complicated part, because of course we know that there's also a lot of gas in the systems, and this gas retains some angular momentum even in the vicinity of the black holes, and it forms a so-called circumbinary disk, which is shown here in this figure at the bottom. Now the dynamics are extremely complicated and depend on the thermodynamics of the gas, on the orbits, of course, on the masses, on the mass ratios. And so a lot of work is needed to understand exactly the dynamics between the binary and the disk. Also because many studies have provided negative torques or positive torques, depending exactly on the configuration of the system. So this is one of the most important aspects where we should really improve the complexity of the studies. So moving from two-dimensional to three-dimensional, including MHD, more complex thermodynamics, radiative feedback, and so on. And together with the presence of a circumbinary disk, also important may be the mini disks, which basically are very small disks around the two black holes of the binary. They might not be very massive, and they be even intermittent, but they could be very important for the growth and the accretion of the black holes themselves. And of course, they would have also an effect on the black hole spin. So related to this, to the presence of a circum-binary disk and also of the mini disks, of course, there is the effect of AGN feedback. There have been some recent studies, like for example, by Del Valle and Volonteri, that basically showed that depending on the gap regime, if there is a gap or if there isn't a gap, this feedback could actually be important. And in the case when there is no gap, actually AGN feedback will be important in creating basically this so-called feedback gap, which could hinder the hardening of the binary. In that case, the feedback was isotropic, and so of course feedback is more complicated than that, so more work is needed in this respect with, for example, collimated feedback and interplay with star formation. And finally, another complication is, of course, the existence of triplets and multiplets of massive black holes. And this is a natural outcome of the fact that actually it's not so easy to form black hole pairs and black hole binaries. And so basically, a third body would have the time to basically reach the host where a black hole pair or a black hole binary is formed. Or even you could have two hosts, each with a binary, and in that case, you would have a quadruplet. And the dynamics of these systems is inherently chaotic, of course. And so a lot of more work is needed to understand exactly what happens in these cases. And we should also include the triple and multiple interactions in models of black hole evolution. And to conclude, if we manage to pass the first phase of dynamical friction and the second phase of stellar hardening, then we basically get to the relativistic evolution, the gravitational wave driven in spiral. There have been a lot of work on this, especially using post-Newtonian approximations. There has been a seminal work, for example, by Peters and Peters-Matthews in the 60s. These approximations are actually very good, up to down to maybe 10 gravitational radii. And then we need the full general relativistic simulations, and probably a lot of work has to be done in this respect in the next 10 years on that. Sometimes all we need is a gravitational wave in spiral timescale. And for that, in the past 60 years or so, almost everybody has used the Peters timescale. But there are now more accurate timescales that use higher order post-Newtonian terms. And probably this more accurate timescale should actually be adopted, for example, when calculating merger rates for LISA. And finally, the final outcome of the black hole coalescence is the kick or the recoil of the binary because of conservation of linear momentum. And these kicks can be extremely large. They can reach thousands of kilometers per second. And ideally, if there is some gas around this remnant black hole, we hopefully should be able to see some electromagnetic signatures. And there is already work done in this direction. And if we were able to actually confirm these candidates in the next few years, then we would have some proof that actually this massive black hole coalescences really exist. Okay, my part is done. I'll leave the mic, I'll leave the floor to Melanie. Just. Okay.
Yeah, perfect. Okay, let me go to the screen. Can everyone see the screen and the mouse?
Yes.
Okay, perfect. Yeah, good morning, everyone. Yeah, so about a third of the chapter was dedicated to massive black hole origins, growth, and also prediction and the merger rate that Lisa could see. And I guess that's the most important thing. So I'm going to review a little bit of what was described in the paper. It's not going to be an exhaustive list because it's truly impossible. But those sections nicely really describe our current understanding, also highlight unknown on those physical processes, and also give, describe the limitation that we have in the current techniques that we are using and also directions for the LISA community, and broadly speaking, everyone, to actually improve what we have at the moment. And thanks again to all those people that participated to those sections. So let me start with black hole formation. So here you have the redshift as a function of the mass of massive black holes. So in the local universe, the mass of black holes go from a few 10 to the 4 all the way to 10 to the 9, 10. And as we go to higher redshift on this cartoon, we are limited by only detecting the most massive and powerful objects, such as high redshift quasars. So what we want to understand in black hole formation is what are the progenitors of all those black holes that we see. So at the moment, we have 4 big mechanisms that are described nicely in the paper, and they predict the formation of black holes either before the first galaxy, for example, with primordial black holes that basically are high contrast density perturbation that will collapse upon themselves at very high redshift. And you see that the range of initial mass here is pretty large. Or mechanisms that will predict the formation of black hole seeds in galaxies or within the first galaxies. And this is the case here with those 3 mechanisms. So black holes can be the remnant of the first massive POP3 stars at high redshift. They can also form as the result of runaway collisions between stars in compact clusters, or with stellar mass black hole collisions as well. So this is a second scenario here. Or black hole seeds can also form from the collapse of a supermassive star that would be formed in very specific conditions. I'm not describing more because we don't have time, but that's basically the diversity of mechanisms that we have today. So those models determine the initial mass of black holes. So you can see we have really different initial mass here, and also the abundance of black hole. And this is key because for the LISA merger rate, we need, as a function of whether you form a lot of seeds or only a few, you will have very different predictions for the merger rate. One thing that makes the picture even more complicated is that those models are not mutually exclusive. At least theoretically, it could very well be a combination of those mechanisms that produce a population of black holes that we see today. So this is also something that needs to be considered. And all those mechanisms, and this is highlighted in the paper, have advantages to explain observations, but also hurdles that make them a bit more unlikely to explain some subpopulations of the observed black holes. So for example, for the POP3 remnants, we think theoretically that this model can form a lot of seeds, but there would be what we call light seeds. So their initial mass is not that large. So they would probably have a hard time sinking to the center of galaxies, making accretion maybe not an efficient process, and same with merger with other black holes. So a lot of caveats for the efficient growth of those black holes. This could be a bit easier if seeds lived in cluster, because the cluster can retain seeds, but we also have to consider recalls from the many mergers that happen in this given mechanisms. And for the direct collapse model, it has been very appealing over the year because it's forming very massive seed, which make it easier to produce a high redshift quasars. But on the other hand, many studies show that there may be only very few direct collapse black holes in the universe. So then we have to come up with another solution to explain that all massive galaxies in our local universe have a central black hole. So for the next step, the paper was listing 2 big things. That the first one is that we need to reduce the uncertainty on the seed number density. At the moment, we have some ideas, but it's not clear exactly how many black holes would form out of those mechanisms. And we also need detailed prescription for those mechanisms that we can also use in different techniques when we compute the black hole merger rate. Okay, and then the paper described the growth of black holes. So there are 3 questions that are tackled particularly. So the first one is how black holes grow in time. So what is the contribution of accretion, gas accretion versus black hole mergers? What is the impact of black hole growth on the spin of those black holes? And what do we actually learn by observing the spin of black holes? So I'm going to be very fast on the spin part. There is a strong link between black hole spins, the radiative efficiency, the accretion, the growth of the black hole, the feedback, the possibility of having a jet. So all of this is very strongly linked, and that's why it's so difficult to actually model all of this self-consistently. But given that spin are our very best chance to diagnose the accretion history, we need to improve this different techniques. So there have been a lot of improvement over the year for both semi-analytical models and simulation, where now we really try to model the spin, the evolution of the spin as a function of the accretion disk or like the accretion flows. And this is, we're on the good track, but there is still more work to do. So we need a realistic spin distribution that will be key for LISA. We also need to model further the spin in the cosmological context. So how does the spin depend on the accretion disk, on the morphology of galaxies, the redshift? How does it impact the feedback? All of this. And the paper was also stressing that we really need to look at correlation with spin that is observed with electromagnetic observations. Although those are for the end of the LISA band, but still a very interesting correlation there. So this is one thing that would be nice in the coming years for sure. Okay, so what about the accretion versus merger for the growth of those black holes? So here we're showing the redshift as a function of the mass of the massive black holes. And the color here is an indication of whether the growth history is dominated by merger, in which case we're in this red area, or by accretion over time. And this would be the blue part of the diagram. So here, really, the growth history of the black hole seeds will depend on their initial mass. So if we start, for example, with low mass seeds or light seeds, they would probably have a hard time sticking to galactic centers. So their accretion wouldn't be that efficient. So this is one key parameter here. Those light seeds, they may be more impacted by supernova feedback, for example, because every time you have a supernova event, you will deplete the black hole gas reservoir. So the black holes will not accrete for a given time after supernova. And so this will also lower down the accretion into black holes. Super Eddington growth is a possibility, but what kind of condition do we actually need to see this happen? That's one of the big questions. And depending on the mechanisms to form black holes, we'll have many black holes or just a few. And so the merger rate will also depend on whether black holes are abundant or not. So basically for small black holes here at high redshift, what we see from this paper is that it's basically 50-50 on the accretion versus merger contributions. For slightly more massive seeds, the growth could be easier because they can sink to galaxy center. But what we want is to keep those black holes in the LISA band. If they grow too much, then we won't observe them at high redshift. So for this point, supernova feedback or even the feedback from the black holes can help us by decreasing probably the accretion rate into those black holes, so we can keep them in the LISA band. So the paper described nicely all those questions and what we have to do to improve those points in the future. Okay, so now if we want to compute the merger rate for LISA, we have to solve this what I call the LISA puzzles. So we have to capture so many physical processes that it's actually very challenging. So I kind of try to summarize here those different processes. So we have the formation of black holes. So what is the initial mass of black holes? What is their initial abundance in the universe? And then, of course, we need to model the growth of black hole. We need to model black holes dynamics, ideally, both things that we can resolve, like dynamical friction, but also we have to find ways of modeling what cannot be resolved in our current techniques. So everything that is at smaller scale than dynamical frictions, basically. The spin needs to be self-consistently linked to the growth of black holes, but also the feedback. So that's also a very challenging point. We want to do this in a cosmological context because, of course, the universe is evolving, so we need to consider this. We want the properties of halos and of galaxies to really understand in which environment those mergers will happen. And we also want statistics because LISA, it's going to cover the full sky. So of course you don't want to do this only for one galaxy. You really want to understand statistically what is the merger rate. And probably there are other things that we haven't think about yet. So this is going to be the missing piece that I put here. So really we have to resolve all of this. So at the moment, of course, we cannot have all of this in our techniques, but we are, slowly getting there. So the chapter really nicely described two techniques to derive the merger rate. The first one is using cosmological simulations, and the second one is using semi-analytical model. So cosmological simulation, they evolved the universe over a cosmic time. They resolved kind of self-consistently the evolution of galaxies and their black holes. The spatial resolution is about 1 kiloparsec for big simulations, so very large volumes, such as Illustris or Horizon HN. And you can achieve 10 parsec resolution if you're really doing a small volume or a zoom-in simulation of a few galaxies. The nice things with simulation is that you include a variety of environments. You really have, you capture galaxies over the mass spectrum, same for the black hole, so you can really look at different configuration, different environments. But unfortunately, it's really expensive computationally, so you cannot run the same big simulation several times to understand, what would be the different merger rate if you change the seeding of the black holes. So you always have to choose as well between a large volume and a high resolution, which make it also difficult. And sometimes, always, you do not resolve, in most of the cases, small halos where black hole formation could actually happen. And so you're missing a piece of the story. And some simulations also do not resolve fully the LISA black hole band, which is also a caveat. On the other hand, semi-analytical model, they evolve black holes and galaxy with the properties of dark matter halos, so everything is really tied to the halos. And the merger rates of the merger history, of halos is you can get it by using a precious formalisms or just using a dark matter simulation. So that shows the spatial information as well. So it's nice because you can probe smaller and larger halos than in simulation. You have a bit more flexibility, and you can, because it's not computationally expensive, you can really test your modeling and the different assumptions that you're making for seeding, for growth, for feedback. So you really have this flexibility of exploring the parameter space. Caveats, you may lack spatial information and large-scale environment in some of those semi-analytical models, and you will also be limited by resolution. So in any case, if the techniques is not resolving small halos, and then the merger rate that we derive is always a lower limit of the real merger rate. And I think this is important when we consider what LISA could see. Okay, so before actually showing some of the results, I just wanted to highlight some of the next steps for the LISA community. So the paper really tried to have all those aspects described and what we need to do now to move forward. So for the seeding, the paper is stating that we should use high resolution, but still keeping a fairly large volume, a simulation on some with the physics of black hole formation. So this means really going to the theory of those mechanisms and try to implement them to follow them as much as possible. So for example, by tightening the formation of black holes through local gas properties and larger scale environment in some of the mechanisms, allowing several black holes in galaxies. That is not the case in some simulation at the moment. For filling, we may want to change some of our current common assumption. For example, the Bondi accretion. That is a big assumption that we may want to try something a bit less, I don't know if that's less spherically symmetrical. But also the Eddington limit that is used in simulation, we may want to allow for super Eddington accretion, increase the resolution in the inner part of galaxies as well, while keeping the rest of the simulation with a lower resolution is something that is a direction that we can investigate. And of course, having a spin evolution in the simulation connected to black hole feedback would be also key. And of course, the dynamics of black holes. So for example, having triple or multiple black hole systems, the recalling black holes, not positioning black holes to potential well in simulation, for example, improvement like this and dynamical friction from gas stars, dark matter, et cetera, et cetera. So some works are already doing this, some aspect, but I think we need to move on to really doing this in general to improve the prediction and the merger rate. So this is really needed to understand the degeneracies between formation growth and dynamical evolution. and to predict really what LISA will be able to see. Okay, so the paper is actually summarizing pretty nicely what has been done in the literature. So we have actually a really nice plot that make a summary of this. So I'm going to describe now the merger rate from cosmological simulation, that is the first technique, and then the that is predicted by semi-anticlosed model, that is a second technique. So here we are including all the black holes, not only the one that are in the LISA bands, but still the conclusion are the same. So every line is showing a given simulation. The top panel is showing what the simulation is predicting. So you can see that there is an order of magnitude or more, basically, for the merger rate at fixed redshifts. And then the bottom panel is showing when we're adding delays in a post-processing fashion. So you see that when you add delays, of course, the merger rate is decreasing by a lot. So this is this red line here, where we are significantly reducing the number of merger. So there is no consensus in those studies on the different delays that have been added post-processing. So you can use fixed delay. So you have your simulation, a galaxy merger happen in the simulation. The black holes will be merged immediately. So then you can just say add a fixed delay for the black hole mergers. But you could also have physically motivated delays as a function of, for example, the galaxy properties or the environment and so on. So there is no consensus in the literature. Different papers do different things. One thing that I was talking about is that if you take a large-scale simulation, for example, the blue line here, that is always on HN, that it's a large volume, so you do not resolve, for example, the assembly of low-mass galaxies, but then you re-simulate only a fraction of this volume, and this time with high resolution, so that you resolve those low-mass galaxies. What you see that the merger rate is increasing because you have merger in those low-mass galaxies, so we have to be careful what we actually resolved when we predict the merger rate. Yeah, so when you add delays, you lower the black hole merger rate, which makes sense. And then also this, because we are forced to use those delays post-processing, we are missing the consistent evolution of the black holes between the time where the simulation is actually merging the black holes and the time where they would merge according to our delays. So there is an amount of time where we do not self-consistently resolve follow the black hole evolution. Okay, so now in semi-anticlosed model, so it's showing the same thing, but now we divide by heavy seed mechanisms and then light seed at the bottom. So what you can see that the merger rates are also different as a function of the black hole formation mechanism. So the takeaway message from this, what the LISA merger rate is driven by growing light seeds. So not that much by the heavy seed that are more rare, but really by the light seed that start growing. So you can see here with those different lines that there is not that much consensus for the merger rate either in semi-anticlosed model. One thing that I wanted to highlight is the role of supernova feedback. So from this blue line here at the bottom to this orange line, this is when we include supernova feedback. So it can also drastically reduce the number of mergers. So there is no consensus. So now I think it would be nice to really go back to comparing the simulation and semi-anticlosed models, as it is actually nicely done here, but as a function of really the assumption that were done in those different modeling. And this will help us to interpret the degeneracies. So this is what we should do now. That is the first one of the projects that will be discussed during this meeting. It's comparing the prediction of merger rates from semi-anticlosed models, empirical models, and simulation as really a function of what we put in those models in terms of the formation of black holes, the accretion, the dynamics, the feedbacks, the physics of galaxies, so basically everything. I think one thing that we should do after this first project is to understand the properties of galaxies, where the mergers are going to happen. And I think this will be important to identify Earth galaxies and redshift of LISA events for also the multi-messenger studies. So knowing the most likely galaxies would help. And we can do this as well from cosmological simulations, semi-anticlosed models, etc. And then on a longer time scale, the paper also describes very nicely that we will have to identify the best strategies, because we want to follow a lot of different processes while keeping the cosmological evolution of the universe. But also we want a large volume because LISA will cover the entire sky. But we also want to keep the possibility to test rapidly different assumptions that we are using. So the parameter space of the assumption, but also unresolved aspects. So we will have to come up with techniques and can do this in a relatively short amount of time. So the paper is also describing new techniques of how we could do this in the future on a longer time scale. And I think that's it for me.
Okay, so thanks for the presentations of Pedro and Melanie. And now to finish, I'm just going to describe a little bit how LISA can be used in concert with other missions to really do our best to understand the massive black hole population across different redshifts. And I want to apologize in advance. I'm far from expert on the topic, so be forgiving to me, and please also correct me if I say something that is not really correct, okay? So first of all, I think it's interesting. Also, this is what happened in the white paper. We really divided between two different kinds of multi-messenger observations, because on the one hand, we can really observe a source with LISA and then use all the facilities we have, point towards the same source and try to get the most out of a single source observation. This is the coincident observation. And on the other hand, we can also take a more like a population-based approach and observe stuff with LISA, but also observe the black hole population via other missions, other black holes, and put everything together to build really our nice catalog about the black hole evolution across the evolution of the universe. And I think it's important to really stress that while coincident observations need to be done when LISA is there, the population studies can really start already now and can continue after LISA. So this is really like the time to work on it. So before like going into all the possible facilities, I thought it would be nice to really recap a little bit what are the observational evidences we expect from merging binaries. So first of all, we have theoretical predictions that suggest that the light curve of binaries, especially if they are at a slightly sub-parsec scale, that would be modulated over multiples of the binary orbital frequency. So actually nowadays we have a lot of observational efforts trying to find modulations in the light curves, and we have a lot of candidates. The problem of those is that this modulation in the light curve is not a unique signature of binarity, and this modulation can be due to other kind of, periodicities in the single AGN itself. So one important thing to be done in the future is, first of all, better understand the periodicity of AGNs, even if there is no binary, and also work on the theory and both theory and observations to find what can be a unique signature of binarity to really distinguish a candidate. There are other approaches that work at those scales to find binaries. For instance, one can try to really observe the velocity, the large velocity difference between the broad line region closer to the black hole and narrow line region that is at rest with the host galaxy, find time varying shift of broad lines and other spectral features. The problem is that all those strategies are going to actually find progenitors of LISA sources because they work at large masses and low redshifts, but especially at too large separations to be in the LISA band and to merge within the LISA time frame. So if we want to really make a proper multi-messenger detections, coincident detections, we have to go to smaller scales at which we expect different signatures. For instance, there is the broad iron emission line that can already be detected nowadays that is emitted very close to the black hole. And also with the future X-ray facilities like Athena, we can look at much higher redshift and find this emission line. Also, we can find the fact that the multicolor AGN spectrum has basically suppressed part due to the cavity that can be formed if there is a binary. So we can look for binaries looking for those feature, and also the material that falls into the cavity and reaches the mini disks that form around the binary can be also observed, especially in the X-rays. And together with that, we can also use imaging, not only spectral analysis. Imaging can be used with VLBI, even the Event Horizon Telescope and future radio facilities to really image basically the black holes themselves, or basically the jets that are emitted during the inspire. When we reach really the merger phase, the problem is that we have to work a lot on the emission signatures because we don't really know what is going to happen in the electromagnetic band when black holes merge. So in particular, we expect X-ray emission from the mini disks. We expect that jets can be launched, and especially during the merger itself, the jet can be rebrightened, can align. And in this very moment, since the jet also accelerates astrophysical particles, we can also have a particle detection coincident with the LISA detection. And of course, during the merger, we can have a kick that is possibly really impacting the material around, so that this can result in electromagnetic emission. But the point is that we don't really know how the material behaves in such a strong gravity framework. And so it's very hard to work out the theoretical predictions about the signatures. And so we need to work a lot on this topic, actually. And if we want to make coincident observations of LISA sources, actually one important, very important thing is the localization. So we all know that the LISA is not a great tool to really localize in advance the merging binary. So there is this very nice work by Alberto, who's actually here, that basically tells us through this plot that only light and nearby objects can really be traced along the spiral before the merger. And so this will pose a challenge if we want to start pointing at the source before the merger happens. And we have to work out strategies. For instance, in principle, one can use, first of all, large surveys like LSST, Vera Rubin Observatory, that has a large field of view, to scan the sky, find the possible position of the source in a much narrower region, and then this can be scanned again through the Athena mission that hopefully will tell us a lot about can detect the X-rays emitted during coalescence. And if those two missions that are still in the proposal stage, which are called Axis and Links, will actually happen, those will have like a much better capability than Athena in how deep they can go in flux. So those can also help in the multi-messenger observation of the pre-merger stage. And at the merger, actually, instead, the localization is going to be much better because it's going to be of the order of 0.1 square degrees for most sources. So the after merger multi-messenger observations are probably going to be easier to perform. Also, in this framework, I think there is this very interesting point to touch upon, which is the fact that if we will have these axis and links X-ray observatories, and then we have LISA, and then at some point we will also have the Einstein telescope. Those observatories will all be together able to detect the starved black hole seeds in this mass range between, let's say, 10 to the 3 and 10 to the 4 solar masses below redshift 5. So we will be having hopefully coincidental observations of those objects. And now let's go a little more into the all possible observatories that can work together with LISA. Here it's like a subset of them in this list. In particular, at the top, we have like a time frame of when those facilities will be happening. We have many in the X-rays. We have other gravitational wave facilities. We have infrared, optical, and radio observatories. And a chunk of them are going to actually be sensitive to the range in which LISA will operate. So this is very good news because in principle we can really hope to detect and constrain the black hole population through those missions. And in particular, going a little more into the detail and also not just focusing on single sources, but on the whole black hole population, we will have a gravitational wave detections, for instance, through the pulsar timing array, Einstein telescope, cosmic explorer, and in principle also through astrometry via Gaia that can also help detecting gravitational waves at 10 to the 8-ish solar masses. And all those together will really help us understand at different redshifts and different masses where black holes reside, the merging one at least. Instead, if we go to the multi-messenger electromagnetic detections, we can have, I already mentioned Athena, Lynx, and Axis, the already operating eRosita that can try to detect not only binaries, but actually all the accreting properties of AGNs that exist out there up to very high redshift, as you can see from, from this plot up to redshift, for instance, 4. And also we can have studies of the galaxy hosts. So the galaxy hosts are important if we want to understand the interplay between the growth of the black holes and their galaxies they're embedded in, and we are going to have DESI, JWC, Roman, Euclid, for instance, and many others that are really going to tell us a lot about what are high redshift galaxies. And also other observatories like the ELT and 30-meter telescope could shed more light on the assembly of those first galaxies and how they aggregate. And more like in the optical and radio band, we can have LSST, SDSS5, SKA that can find new binary candidates and in general study the AGN population across different redshifts. So very quickly, we will be able, I don't have time to go through this list in much detail, but in the end, by combining all those tools, we'll hopefully be able to really understand, first of all, how the first massive black holes formed, to track their growth across the cosmic times, to really understand the co-evolution between them and their galaxy host. So if they really evolve in a symbiotic way, what is the effect of AGN feedback? And also to connect the large-scale structure and the merger rates in the LISA band. So, for instance, to understand in which kind of environments we can detect more galaxy mergers, between groups, clusters, and so forth. And also, of course, through combined electromagnetic emission, we can also really understand better how gravity behaves how matter behaves in the strong gravity regime and other signatures that I already mentioned before. So this is like a very summary slide with the next steps for the LISA community. Most of them were already mentioned. I just want to add on the top of them that we should, and we are in some extent already doing it, we should use an artificial intelligence to really help us in this really ambitious job of making catalogs and, for instance, constrain LISA source parameters. So I have to rush a little bit, but this is just to tell you that I believe I'm impressed by the long way we have gone in our understanding of massive black holes. If we think about how it was 50 years ago, it's shocking. But there's still a very long way to go, as we try to convince you. And LISA will help a lot in the next years. So thank you.
Thank you very much. Thank you very much. So Valeria just sent in the chat a link where you can write down your questions that you have for the speakers of this. So I will set up. So the next talk, we will have 3 short 10-minute talks. Now the first one will be by Gianluca Calcagni about the LISA Internal Networking Committee for Science. Let me just set up here, and then I will
Technically.
Can I already start to share the screen now, or not yet?
Yes, we can hear you very well, Gianluca. You want to share your screen? Seems to be working. Yes. Yes.
Okay.
So, please go.
Okay, thank you very much for this kind invitation. Today I will briefly describe a new group inside LISA, which is the LISA Internal Networking Committee for Science, LINKS in short. The need of such a committee arose because we are getting many. Presently, the consortium counts more than 1,600 members, subdivided into 101 internal groups and 200, almost 230 external groups. And in particular, the LISA Science group constitutes more than 2/3 of a consortium. So internal coordination and information accessibility is more needed than ever now, but it requires some sort of organization that we didn't have before. So the structure of a LISA Science group is not easy to summarize in 1 minute, but it's publicly available. And to find it, you can just go to the web page of a sign up for the LISA consortium, which is freely available to anybody, and it has this URL. And at the bottom of the page on the right, you will find this description of LSG work packages. So there, which is the so-called Edinburgh document, you will be able to find all of the information about the recent restructuring of the LISA Science Group. So people often want to collaborate, to contribute to certain work packages, but do not know how. So this is one of the reasons why we created the links, and the email for any further question is this LSG -links@lisamission.org. This committee started in October 2021, And originally it was meant to have a fixed duration of about 1 year, but we have been realizing that there is so much work to do that we will probably request an extension to complete some of the tasks. So the chair of the group is Elena Maria Rossi, who is also chair, one of the chairs of ELISA science group. And the members, apart from myself, are Anna Heffernan, Shane Larson, Jess McIver, Gijs Nellemans, and Marta Volonteri, and David Vai. We meet bi-weekly, except now in summer that we have a more rarefied schedule. So the objectives of the links is, first of all, to streamline information flow within the LSG and between the LSG and the rest of the consortium. Second, to increase and ease the participation to work package and working group activities by sharing information in a more efficient way, for instance, through a new newsletters. And finally, to facilitate the training for new LSG members. Though we do not organize the train by itself, but we help to organize it. There is also a wiki page in the ELISA wiki where you can find information about links, and you can access through this website. And you have to use the same username and password you have for the ELISA directory. So in case you don't remember how to what your username and password are, let me briefly recall. You just log in, you go to the directory page, which is directory.elisamission.org. Note that you have to put the S here in the HTTP. And then you type your username and password, and from there you access the directory. You use exactly the same credentials also for the wiki, for the ELISA wiki. If you don't remember username and or the password, you click here on I forgot my password, and by introducing your email address, a link will be sent to you with a reminder and a possibility to reset your password. In case you don't even remember the email address with which you registered in ELISA, please write to the management membership and management team at mmt@elisamission.org. Now, this is a sample of information you can find in the links page, which is a collection of websites associated with ELISA, and the way to register to these websites and what these websites are for. For instance, the ELISA directory, which we talked about right now, Atrium, Slack channels, GitLab, and so on and so forth. Recently, the chairs of LSG also promoted the initiative of a quarterly newsletters. There are 2 issues now, November 21 and March 22. And there is a lot of useful information about ongoing projects in work packages and on the contacts which you should reach if you want to contribute to these science projects. Finally, some activities in progress by the links are the following. One is reorganizing the wiki page, then building a page of frequently asked questions about the platforms, about the ELISA functioning, and so on and so forth. When we are also collecting, although unsuccessfully, I have to say, information about Slack channels presently used in a working group and work package activities. And then we are also trying to support the organization of training sessions attached to consortium meetings, which focus on topics of relevance to the ELISA science group. Example is the LDC workshop. Finally, we're trying to streamline how to get involved in ELISA scientific activities. In particular, if you do want to get involved, we suggest first to check the LSG newsletters, then to contact directly the work package chairs, which a list of which you can find in the wiki page, and as a last resource or as a first resource, depending on the point of view, you can just directly contact us at the email I wrote before, and I remind you is lsg-links@lisamission.org. So thank you very much.
Thank you very much. So we even have time for a few questions. People want to ask. Gianluca? Doesn't seem to be the case. So just to give more time to the rest of the speakers, I propose we move on. The next talk is going to be by Elisa Nacho.
Hi.
Hello. She's going to talk about the LISA Early Career Scientist Working Group.
Yeah, thank you for the invitation and for the opportunity to discuss about the LISA Early Career Scientist Working Group. So I am one of the 3 chairs of the working group, and today I will talk to you about the activities that we have been doing, and I will invite you to subscribe to this group if you are interested in this. So this group started 2 years ago, and it has lots of members. Now we are 234, and this number is growing day by day. And everyone who consider themselves as an early career scientist can subscribe to the group. And there is no strict rule on the number of years after PhD or other criteria. And the scope is to discuss needs and values shared by early career scientists, support also the career development through job and grant applications inside and outside academia, foster collaboration among people, especially for new members or people coming from different scientific backgrounds, and also promote the participation of early career scientists in leadership roles, outreach activities, and so on, and essentially lay the foundation of an inclusive working environment within the consortium. And as I mentioned you before, now we are 3 chairs, and we have been elected in January of this year, and the mandate is for 2 years. It is done with online and democratic elections among all the LEX members. And we also have a diversity rule for which, based on gender and the career stage of the chairs, so at least 1 chair should be female, and at least 1 chair should be a PhD student. And so far, during these couple of years, we have organized many activities, and by we, I mean all the LEX chairs of the previous years, but also just volunteers within LEX who brought up some new and interesting ideas and projects we could carry on. So an interesting project is the mentorship program that the first pilot program started last year, and we will continue this in the next years. And there were also some workshops on funding opportunities and available open positions. There were also some webinars on soft skill trainings and LISA data analysis, and webinars on stress and mental health in academia. And there is also a task force to discuss about sustainable LISA mission. So just for lack of time, I will not go through all of these activities in detail, but feel free to ask questions if you are curious about some of them. So about the mentorship program, this started last year, and the goal is to support early career scientists on an individual basis. And we asked the consortium members to volunteer for role of mentors, and we had 30 volunteers. And then 20 mentees wanted to run the program. And there was a first kickoff meeting in September, and then the pairs, mentor mentees, could meet on individual basis. And the program lasts for 6 months. Now we will start a new call in July, so stay tuned if you are interested in being involved as a mentor or as a mentee. And also, we had several online workshops on funding opportunities. For example, we have regularly in fall an online job fair where all the recruiters are invited to present the open positions, and all the early career scientists can present themselves and interact informally with the recruiters. So this is also a program that is run now yearly in the period in which most of the open positions come out. And for example, we also gathered some shared resources. So we have a spreadsheet where there's a list of all the available fellowships for early career scientists. And they are cataloged depending on their country, application deadline, and so on. So here there are the links. I will share the slides. You can also look at the links if you're interested in this. And you can also add some of the missing fellowships in some countries. And also we have a spreadsheet with LISA host institutions, with people working in these places, and this is useful for visiting periods or getting to know about other groups within LISA. So starting from this year, we would like to run a second mentorship program. Stay tuned, and as mentors, we would like to have a diverse pool of mentors that also have different experience and different career stage. And as new projects, we have started a new software series where early career scientists who have developed some open softwares can do tutorials. And we are collecting in our wiki the ones that we have already done. And then we are starting the project of cross-disciplinary talks, where during our telecons, early career scientists can discuss about their research in an informal environment and practice for talks. So if you are interested in this, we are looking for volunteers, and you can send an email to the Lex chairs for volunteering. And also, we are interacting with the other early career scientists in the other communities like LIGO, Virgo, and PTA. So a new organization has just started called WEX. And here there is a link for the website, and we also have a mailing list where you can subscribe if you are interested in participating or attending common activities we are organizing with other early career scientists. And also, as another resolution, we would like to increase the presence of early career scientists on social media. So there's a new LISA social media team who has recently developed lots of content, and will be happy to have more involvement from early career scientists. So in general, if you would like to join the group, you can send an email to the chairs, and you can be added to the mailing list, to the wiki page where we gather all the information, and to the Slack channel for informal communication. So feel free to ask questions if you have some about our projects. Thank you.
Thank you. Does anybody have a question for Elisa? Early career scientist. No, then thank you very much, Elisa. And our next speaker is going to be Gijs Nijmans, if he's here. Hello.
You're muted, Gijs. I couldn't hear you.
Okay, let's try this.
That works.
Okay. I keep having trouble with my sound since yesterday.
It's working well now. So,
all right.
Is he going to talk to us about the Red Book?
All right. Hello, everybody. Nice to see you. I'm afraid I'm not in Birmingham, which I think is a shame. But anyway, there's nothing that can be done. Sorry, I was distracted because I thought I could see the big screen with the room in Birmingham big on my screen, but that's not true. So I see you as a host stamp. I will say a few words about the Red Book, but before I do so, I have to take a step back. And so, as I hope most of you know, Lisa has passed phase A successfully and is now in what's called phase B1. It doesn't really matter so much what all these acronyms mean, but the important thing is that we're now working towards what's called adoption, and that's the single most important point in time of a space mission, because it means that ESA will approve significant funding of the order of 1 billion euros. And essentially that it means the mission will be started to be built. And so this adoption is not, as we were told recently, it's not a calendar date. It's really something, a threshold that you have to pass. And there's basically three things that have to be correct. The science has to be compelling. The technical case has to be feasible, and the programmatic has to be feasible, which means that there is enough money. People are willing to spend the money and to take responsibility for some parts. In the European setting, that's mostly the member states, but it's also means a formal agreement between ESA and NASA. One other thing that's important to note, I think, is that at adoption, in principle, the data policy will be determined because there is a formal document called the Science Management Plan, which will have this data policy. Okay, so how does it work? There is an advisory structure within ESA, within astrophysics working group. I think AWG it's called, so it's a bit called like us, but it's called AWG. There are other working groups, they advise to what's called the SSAC, the Science Something Advisory Committee, and they then advise to SPC, which is the highest body that has to approve. And so to do this, a big document is written, which is has a formal name, but it's known by everybody by the name Red Book. Where essentially as science objectives translated into science requirements for the mission, then a description of the mission concept and instruments, and then something about how you get from data to usable science products and how things are organized in the, with the data processing and the ground segment and the management and all these kind of things. And so this is now written. Who is doing this? The formal interaction between ESA and the community is via a group of people that is called the LISA Science Study Team, SST. And I listed the members here. Many of these will be well known to you. All but two are very active members of the LISA Consortium. But to be very clear, the LISA Consortium is not the partner of ESA in terms of the community, only in terms of providing hardware, etc., to ESA. And so this science study team basically has to take charge of writing this Red Book. All right, that was a pretty long introduction to the important part here. And so the science objectives is the biggest part of that, or a significant part of that red book. Monica Kolpi and I will coordinate writing this. And we have to find a balance here because, of course, Lisa has been selected, I think is the official name, and so has been studied in the ESA context based on this document shown here on the right, the Lisa proposal. And so in principle, all the hardware is designed to meet the science that's written in that book. So we should not write a completely different science case because that will be very confusing. And so we'll stick quite close to that. But of course, we use the white papers, including the Astro white paper, to see sort of updates with respect to the 2017 state of the art. We have already a lot of experts in the SST, but it may be that there will be a call on some of you to help with writing this or providing some figures or whatever. However, there's a pretty tight timeline, and so we will have a slightly different approach than, for instance, with the white paper, where we want to keep the teams relatively small, because otherwise, as we have experienced, things take very long. Speed is a bit of the essence here because it has to be ready. And so the bottom thing here is the timeline is that it has to be ready, well, summer 2023, which means we aim at spring 2023. And so that's the timeline. In order to make sure that we actually don't miss important things and everybody can be involved, there will be some round of comments or sharing of the document within the consortium. At least that's what we are thinking of now. That's all I had prepared. I don't know how much talk there is about. There's lots of things going on with the planning of Lisa. If you want, I have a slide on this, but I'm also happy to leave this out. The bottom line is spring 2023 or so for the red book is the target date for us.
Thank you, Gijs. So we still have a couple minutes. Yes, Valeria?
I have a question. Can we fail mission adoption?
Yes. But as it was, the point is that mission adoption is a formal process within ESA. I'd never heard of this, but apparently there is something called the Inspector General, which is a specific group within ESA that actually is doing this. And so the thing is that if we're not ready, we won't go for adoption. And so basically the LISA study team, which is different than this science study team, but there is a team within ESA that is basically coordinating the LISA mission. And I think we have to convince them that we're ready, and they actually have to provide lots of documentation too. And so this adoption process, which has now been moved to November 2023, and so that's this whole business now with the planning. So we have to be ready by November 2023. That's really a short time. And so I think that the worries are not so much on the writing of the red book. I think we can pull that off in, say, a year. But the technology needs to be sufficiently ready that this review will indeed agree that the mission is ready to move to the next stage. And there's a number of open items. And the other quite a big challenge is that there is a plan of who will make what and therefore who will pay for what, but not all the funding is actually in the bank. And ESA only wants to go forward with this mission, of course, if there is a written agreement between ESA and, for instance, Germany and France and the UK and the Netherlands and all the countries where somebody high up in the hierarchy of that country puts a signature. And so that is still a little bit of a challenge to get that all done.
Yes, Thomas?
So guys, this is Thomas. Does this also mean that needs to be a formal agreement with NASA then by next year's early end of next year?
Yes.
Okay. Wow.
And so, you know, ESA is actually talking to NASA, I think, you know, this week in preparation for this, because the point is that these are legal documents. So even if you all agree, it still takes apparently 6 months before the lawyers are done with it. And so, as somebody from ESA said, you know, time of, you know, fiddling around is over. Also, in terms of the technology, you know, working a bit longer to maybe increase the sensitivity a little bit more, that's all over. If it can be done, we have to move forward. And if it cannot be done, we have to find a good way around it. But there's no time.
Another question? If not, then let's thank all of our speakers for the session.
Put her hand up. Maybe you didn't notice, but she lowered it. But
well, if there is time, you had said that you had an extra slide. Can you show it?
I was already wondering why nobody is asking. And so there we go. It's not this slide. This is a timeline which you can't read. And so ESA has found out that the total cost of the L2 plus L3 mission in the current estimate comes out at 3.4 billion. The official reserved amount is 2 billion. The anticipated amount was 2.5 billion. And so this is not possible. And so the 3.4 is 1.9 for Athena and 1.47 for LISA. And so there has been big debates, which is very interesting. But the upshot is that both LISA and Athena are asked to make a plan to fit in roughly 1.3 billion. And for us, it's challenging, but people believe it's doable without making major changes. And so that's the thing on which we're moving. And to be sure, because ESA is not, how do I phrase this? ESA is not sure that Athena can, on a very short time scale, come up with a feasible plan for 1.3 billion. And they absolutely want to adopt one of the two missions, at least in 2023. LISA is asked to be ready for adoption in the end of 2023 rather than spring of 2024. And so there's been lots of discussions and rumors, and people have said, oh, Athena is going to be cancelled or whatever, or this is all not the case. At least that's what they're telling us. And so the plan is still to launch Athena and LISA close together. But maybe LISA adoption now has to come a little bit early, and then Athena a little bit later, which also means that Athena would be launched a little bit later. But they still try to aim having them quite close together.
Okay, so thank you very much. And we have a lunch break now, and we'll be back in an hour. Or...
An hour. And people on Zoom, remember to use a different link.
Yes, the link will be different for the Zoom.